Sorry about the delay. Had some obviously technical difficulties. This project was for one of our professors, Dr. Davis, who has a unidirectional shaker table that he needed basically modified to make it more portable and more usable for his projects. Wylie and family decided they could take it on, and they're going to give you how they solve the problems.
First off, thanks for joining us today. My name is Daniel Taylor.
And I'm Wylie Brown, and our project was the design and construction of a unilateral shaker table. And right here is an example of a Tacoma bridge, but as you know, it doesn't work. And so here it is on YouTube, just a little clip, and as you can see it swaying quite violently in that one. But this is just caused by the wind, and so our project is to help show that you need a design resistance in your project. And at one point, a guy leaves his dog in here and has to go rescue it before the bridge collapses.
First off, why vibrations are important in the real world. Vibration can be defined as a linear motion of a particle about the item's equilibrium's position. Vibration testing includes exciting structures to see how they will respond at different frequencies that are input. There's two different types of vibration tests that are typically used. The first one is a sign test. They're performed to observe the structural response under one frequency at a time, as compared to the second test, which is more applicable. It's more replicated to the real world environment. It's to observe a structural response under more than just one frequency. What is a shaker table? Shaker tables are often used to perform various types of testing, from general vibration testing of components to vibration testing of different structures. A shaker table helps illustrate the importance of excitation and vibration on structures such as buildings, bridges, etc. Some of the requirements for our shaker design that must include the ability to attach and remove the 2075E shaker, allow for assembly and disassembly and breakdown for no more than 5 to 10 minutes.
And this is because it's used in multiple classrooms and they need to move it back and forth easily.
It must allow for alignment between the shaker and the attachment to the table itself within a 15-degree radius up and down. It must remain aligned over the stroke cycle for no more than an inch. Must operate up to 500 hertz without any difficulties.
We actually didn't test it all the way up to 500 hertz, but we just believe it does because it's rated to it.
It must remain stationary while in use. You must build a protective housing to protect the shaker in connection to the table from any falling debris such as balsa wood or Lego blocks. And then we must have a kill switch to help protect the shaker from any overload.
Right here is an example of a shaker table, and as you can see, this is about 3 feet by a foot wide, and this is just to help demonstrate the vibration in the structures. You can see you just mount things to the top of it, and it just vibrates back and forth. And this is used in 2 of our classes here at USI, and in one way they use it to test balsa wood structures, and they just vibrate back and forth until they break. Right here you can see that there are all kinds of different sizes. Some are as big as a car, some are as small as the other one we've just seen. Right here in the bottom, this is the motor we are using. It's just 12-inch motor here. And it's used in different kinds of industries. It's used in aerospace, automobile, in construction, just test vibration. And, but it's also used in laundry rooms. Your washing machine can come unbalanced and it can vibrate and destroy it and your laundry room. Our design included having a waveform that creates a signal and an amplifier, and that's going to run through a kill switch. And then we decided to use a ball slider, which low friction allows the table to vibrate back and forth. And that our motor's air cooled, and then we mounted all together to meet some of our requirements. And then our housing protected.
First off, what is a waveform generator? The University of Southern Indiana supplied us with the Agilent 3210A function generator, as you can see. What we're using this mainly for is to input different frequencies and different voltages at which we can change the excitation or vibration of the entire process. Another interesting thing about the function generator, as you can see on the right, there are 4 different wavelength forms that can be formed by using this function generator. The 2 that are more commonly used or well-known are the sine wave on the top and the square wave. And then the 2 located on the bottom, maybe less familiar with, are the triangular and the tooth waveforms. What is the power amplifier? USI also supplied us with the Model Shop 2050 E09 linear power amplifier. A few things about the power amplifier. It does have 2 different mode of operations that it can operate in. You can set it in a voltage mode or a current mode. On the front, there's a little bar graph that alerts you. It's a bar graph that will alert you how much voltage you have going through if you have it in voltage mode, or how much current in amps that is flowing through the process. On the left, there's a continuous gain knob. With this, once you set the waveform function generator to a specific hertz, such as 5 hertz, it allows the shaker to move at a steady pace, and then as you increase the gain with the knob, it's going to allow the shaker to slowly increase the speed depending on how much gain is inputted through the power amplifier. Another thing on the power amplifier, there is a built-in safety system in this to help prevent from the power amplifier applying too much voltage or too much current through the system. So if it does apply too much, then it's going to automatically shut off.
Right here are some of the things we use. This is a low friction ball slider, and we decided to choose this one because it's fairly low cost. Like that can range from either way, from $100 up to $2 grand. And we chose this because of its dimensions. It's wide enough to support our table, and it has a load capacity of 75 pounds. And then we have our kill switch. We just use an on-off 2-position switch, and the signal comes in, and you switch it, and it kills it.
A few more shaker table accessories. Something that always needs to be used with a shaker is an air cooling system. This one, the specific name is a LaFer air cooler. Typically a shaker can operate anywhere between 40 degrees all the way up to 100 degrees. So anytime that the shaker is being used, it is highly recommended to always use the air cooler. It just has a hose that plugs in, connects to the top of the shaker, and it's just constantly applying cool air throughout the process. Also in the shaker, if you are not using an air cooling system with it, it will eventually shut off, as it does have a system inside to alert it to prevent from any internal damages such as burning the entire shaker up. We also had to build a protectant housing to protect the shaker and the attachment from any falling debris during experiments or tests. We chose Lexan plastic, which is just a polycarbonate motor shield, for cost effective, and it was fairly easy to assemble together.
Right here are some of the parts we had to produce. This is our base, which we attach all our stuff to, and that is 1/2 inch 1020 steel. And we were able to drill and tap the holes, which allowed us to mount our motor, our slider, and our kill switch to. We also decided we were going to put some rubber feet underneath to help protect the table and make it easier to move, because that steel weighs like 75 pounds. And then on the left, we have we use an aluminum block. We use this to raise it up to the center of the shaker table, so it is able to push the table horizontally. And we just made this out of aluminum because it's lightweight, and we just recessed it so we could put a platform on top and attach it. Right here is our flow chart, and the waveform generator that's going to create your signal, that's going to run through your kill switch. As it's on, it's going to continue on your power amplifier, here's our finished product. As you can see, this is our generator that plugs into the kill switch and into the back of our amplifier. You can't see it too well, but our motor's under there, underneath our housing. And then that attaches to our table, which is above our stack. And all that's mounted onto our base plate.
This was the balsa wood setup that the engineering 108 class for Dr. Kissel performed this last week. They had to come up with 3 different frequencies that they wanted to test at to see as far as how the structure would hold up. Granted, it did not make it past the first one that they really wanted to work on, but basically they made the balsa wood out of the structure of what a building. So the bottom layer is like the lobby, since it's a little bigger, and then there are 4 or 5 different floors above it with the same area to act as if it's going to be a real building.
And in this video, you can't see it. The table just moves back and forth, and as the top gets out of balance with the bottom, it starts to break, and it eventually breaks in the lobby. And they actually did it at a low frequency and high amplitude, because at a higher frequency, it stayed more in line with the top and bottom of it. And here's our cost summary. Just some of the products we use were ball slider, kill switch, the raw material, your screws, your rubber stoppers. And that's just roughly $450. And then for the labor we put in, me and Dan worked 15 weeks, roughly 8 hours a week. And at $15 an hour, then we add in our consultants that work about 4 hours. And they're getting $100 an hour. And that brings the total up to around $3,000 for our design.
Some of the price comparison for say is us putting this together ourselves, as far as buying it as one fully assembled unit from say the same company, the model shop. We called and got a price quote for this guy right here, which is the exact same shaker.
It's a little smaller.
It's a little, I think it handles up to 60 pounds as compared to ours handles up to 75 pounds. They said at an estimated cost of roughly $17,000 for this fully assembled and put together. And then as far as us doing it on our own, having the shaker supplied to us through the university, the shaker roughly was around between $3,000 and $4,000 is what we could locate. And then as from the last screen with the cost summary with all the raw materials and the labor and such put in was roughly $3,000. So anywhere between $6,500 to $7,500 would have been the estimated cost to put this together as far as buying it fully assembled, ready to go from the factory. And then some of our designs that included, the equipment that had to be purchased was obviously the raw materials, the steel and the aluminum, the ball slider, the kill switch, the rubber feet that goes on the bottom of the steel plate, the screws, and then the Lexan protectant housing.
And what USI provided with us with the shaker, the waveform generator, the amplifier, and the shaker and the air cooler. Oh, and the platform that you mount structures to.
Again, some of the requirements throughout this project for the shaker design table was to have ability to attach and remove the 2075E shaker with ease.
And that's completed with bolts, bolting it down easily, removing it in 5 to 10 minutes.
Yeah, and then must allow for easy assembly and breakdown 5 to 10 minutes at the most, which when we break it down, it takes less than 5 minutes. That must allow for the alignment between the shaker and the table attachments within 15 degrees vertically up or down. Must remain aligned over the stroke cycle for up to 1 inch horizontally with the ball slider. It must operate up to 500 hertz without any problems, which it is rated, so handle up to 500 hertz. I believe the one that we did some research on as far as for the 17,000, it could handle up to, I believe, 400 hertz. So this one's rated a little higher. And then it must remain stationary while in use.
And that's part of why we went with the steel as a base, just for the weight, allow it not to move too much.
And then we had to build a protectant housing to protect the shaker and the connection to the table from any falling debris, which we chose the Lexan due to
Cheap.
It's a lot cheaper, and then they were testing balsa wood and Lego blocks, so we really didn't need something that would be too expensive, but cost effective. And then the little green kill switch box that we had to protect the shaker from overloading, which is just one switch from A to B, shuts it off, switch it back up to A, and then it starts working as if it was never stopped.
We'd also like to thank Dr. Mitchell and Professor Sprouse and Dr. Davis and, of course, Vincent Frazier and always Don Moore. Next question.
How did you create the 75-pound faceplate?
Oh, the
How did you
steel.
construct it?
We went and machined the holes, and then we had to manually tap them out so we could bolt stuff into it.
So you use a manual lathe or manual mill for that?
We used the drill press.
The drill press, and then the tap the drill set to initially get the whole started.
But yes, we did mill the top off the aluminum, stuff like that to make it perfectly flat.
All right, so who was your customer for this?
University of Southern Indiana.
Yeah, but which faculty member?
Dr. Davis uses it, and so does Kissel.
Dr.
Okay.
Kissel and Dr. Davis are the two that will primarily be using it.
Do you have happy customers?
Yes, he's quite happy.
Until I lived it.
Yeah.
I'm just curious, you said the shaker will go up to 500 hertz. What frequency did you actually test it at?
We
For
went-
the balsa wood tower?
For the balsa wood, I think we roughly got up to 9 hertz,
Yeah.
9 to 10 hertz, and then and then that's whenever the entire balsa wood started moving as one unit in line. And then once we started moving the frequency down to roughly 5 or 6, then it started swaying back and forth like a typical building would before it begins to falter and fall.
We did actually run at higher frequencies, like up to 20.
Sure. And the amplitude of the motion, you stated like 1 inch, is it?
Yeah, it's
plus
up-
or minus 1/2?
Our ball slider can move up to 3 inches, and then
But the shaker can only move 1 inch.
the shaker can only move 1 inch in and out horizontally. And then during the test of the balsa wood, the ball slider was moving roughly right at 1 inch horizontally, and then the structure eventually fell once we adjusted, or Dr. Davis adjusted the frequency down to about 5 or 6 hertz.
Any other questions? Okay, thank you.